Let's just say that the study of rates of change of functions is called differential calculus. We're going to be talking about two different types of studies of calculus this semester. And the first type is differential calculus, which talks about rates of change, which is talking about differentials or differential calculus. So in section 2.1, we talked about the average velocity and the instantaneous velocity. Today we're going to talk about the average rate of change over an interval and how it can be compared to the instantaneous rate of change over an interval. So the average rate of change of f over an interval from a point A to a point A plus h, where h is just a small distance away from A, is simply this. It is the slope between those 2 points. So it would be f of a plus h minus f of a over a plus h minus a. And of course, those a's cancel each other in the denominator. So if I asked you to find the average rate of change of the function, the natural log of x, between x equals 1 and x equals 3, you would simply find the value of the function at 3, the value of the function at 1, and then divide by the input values, the difference of the input values, which is 3 minus 1, which gives us the natural log of 3 minus 0 over 2, which on a calculator or computer gives us approximately a value of 0.3662. Now, the definition of the derivative is when we take this difference quotient, this slope formula, between 2 points that are relatively close together, and we take the limit as the distance between the 2 points gets closer and closer to 0. Now, we can't take the slope of a curve or even the slope formula. We can't use the slope if the denominator of the function is equal to 0. So we always have to have a small little difference in the 2 points. The 2 points have to be really close to each other, but they can't be on top of each other. Otherwise, we would have an undefined limit here because we would have a 0 in the denominator. So what we're doing here is we're taking the difference quotient, which is the change in the output over the change in the input, or f of a plus h minus f of a, where again, h is just a small distance between a and a plus h. And we're looking at this as h gets closer and closer to 0, as the distance between the 2 points at which we're finding the derivative or finding the slope is getting closer and closer, those 2 points. This is called the limit definition of the derivative. The limit as h approaches 0 of f of a plus h minus f of a over h. It is called the derivative of the function f at the point A. It's called the derivative at a point. We write this as this notation. Newton was a very lazy mathematician, and he came up with shortcuts and shorthand for almost everything that he did. For instance, he came up with this notation of limit. So he came up with this prime notation. It's actually said the derivative of f with respect to x is given this. Now, this actually came from his partner, Leibniz, who they worked together for a while. And we're going to eventually in calculus be able to take the derivative with respect to any variable we want. We're going to start with just using f and f of x and f prime of x and taking the derivative with respect to just the x variable. So the domain of the derivative is now a new function, by the way. This function is going to be a new function. We'll talk more about this in the next couple of sections that we talk about. But the domain of the derivative function, this function that is found by taking the limit of the difference quotient, is the set of points in the domain of the original function f for which the limit exists. And it may be a little bit smaller than the domain of f, but it can never be bigger than the original domain of f. So the value of the domain of the derivative is the set of points that are in the domain of the original function, but there might be a couple of points where that have to be taken out, where the limit will not exist for that difference quotient. So it may be a little bit smaller than the original domain, but it can never be bigger. So there are many different ways that we can write this thing called the derivative, or this thing called the slope of the curve, or this thing called the instantaneous rate of change of the curve, or this thing we call the slope of the tangent line to the curve. By the way, all those things are synonymous. They mean the same thing. And we interchange them often as we talk about this thing called the derivative. So let's look at different notations. So here's the first notation that we talked about here. That is f prime of x. We usually call it f prime of x, or the derivative of f with respect to x. Now Newton even thought that was a little bit too much to write, so he sometimes would just write y prime, where the output of the function with the prime symbol, that also stood for the derivative of the y function, or the f function with respect to x. Now, Leibniz didn't like Newton's notation. He liked his notation better, and Leibniz used this notation, which is dy over dx. If you notice on a calculator, this actually is on the notation for a calculator. If you go to the calculate menu of your calculator, you'll actually see this notation of dy over dx. It stands for the derivative of y with respect to x. It actually came from the fact that the derivative is a slope, and d refers to actually what Leibniz referred to as delta y over delta x, or the change in y over change in x, as the two values of x get closer and closer together. So Leibniz likes his notation because it signifies more of the idea of that the derivative is the slope of the curve at a given point, at that point of tangency, or at 2 points really close together. He also used this notation, which again looks very similar, the derivative of f with respect to x. Or he used this notation, which stood for the derivative with respect to x of the f of x function. These are all notations that you might see if you Google it, or if you look on different things in WebAssign. They all refer to the same thing. It is that formula that we just saw a couple slides ago. Let's go back to that. This formula right here, they all refer to this formula, which is the derivative of the function at a given point. All right, so now that we have some notations of the derivative, there's also an alternate derivative definition that looks something like this. And if you think about it mathematically, it actually makes pretty much sense for us. We could say that the derivative f prime at a, at some point a, is equal to the limit as b gets closer to a of, okay, what is that? That is the slope of the curve, or the slope between 2 points, a and b. This is f of b minus f of a over b minus a. That's simply the slope between a and b. So what is this saying? It's saying if we take the limit as b gets really close to a, in other words, the 2 points are so close to each other that the denominator will be almost zero, then we take the change in the output values, that will give us the derivative at a point. If the derivative of the function exists, we say that it is differentiable at x equals a. By the way, the word differentiable will be seen. You'll see that a lot in WebAssign, and you'll see it in on tests and quizzes. People will say, or I will say, is this differentiable? It simply means, does it have a derivative? Can we find the derivative using this formula or the last one? So I wanted to show you a little bit about what it looks like geometrically, this concept of the difference between the average rate of change, or the derivative over an interval, compared to instantaneous rate of change. So the easiest way I could demonstrate this is, think of 2 points on the curve, A and B. Notice here's A and B. where here's a distinct point A, here's a distinct point B. The line passing through those 2 points is the secant line between 2 distinct points on the curve, where h is not really small. It's a distinct difference between these 2 points. The slope of the average rate of change is simply the slope of the curve between those 2 points. It would be here, f of a plus h, here, f of a, those are the output values, over a plus h minus a, which ends up being h in the denominator. So it's simply, I always like to tell students, think of the average rate of change is the 2 points are distinct, pretty far away from each other. And it is the slope of a secant line passing through 2 points A and B that are not near each other. This is called the average rate of change over an interval, or the derivative over an interval. As opposed to the instantaneous rate of change, or the derivative at a given point. Now what we do is we take the 2 points and we hold 1 point. So we'll hold A where it is, and we bring B closer and closer and closer and closer to A, so that the 2 points are so close we can hardly tell the difference between them. And then we can draw this tangent line to the curve, that line that just kisses the curve at a given point. This is the slope of the curve, or the slope of the tangent line to the curve, or the derivative of the curve, all synonymous with each other. The slope of the curve, the slope of the derivative, the slope of the tangent line to the curve, the derivative of the curve, the instantaneous rate of change of the curve at a point A. So here are the 2 explanations side by side. So the derivative at a point A can be interpreted as the slope of the curve at A, or the slope of the tangent line to the curve at A, or the derivative of the curve at A, all meaning the same thing. All right, so before we actually do some algebraic work and do some calculations here, let's just think of it numerically. Let's compute the rate of change of a derivative numerically. So if I gave you this curve where you're looking at the number of fruit flies over a time in days, and the blue curve is this curve over that time period. I also give you a table of values here, so we're looking at it numerically with a table of values. How could you use the chart above to find a good estimate for the derivative at 40? Remember, the derivative at 40 simply means if I went up to the curve and I drew the tangent line to the curve and kissed the curve at x equals 40, in this case t equals 40, what would the slope of that tangent line be? Well, I don't have 2 points that are really close here, other than I could say, well, I could use 2 points close to 40. So I could do something like this. I could say, well, I'm going to estimate the derivative at 40 is f at 45 minus f of 35 over 45 minus 35. So I'm estimating it by using these 2 points around 40. So in other words, connecting here at 35, here at 35 and here at 45, and connecting those 2 points. And I get, by the way, I get 3 flies per day. Now, could we use other points to give a good, is this the only ones we can use? No, it's not the only ones, but this would be a good estimate of how we would find the derivative at 40 by just using the average rate of change on either side of 40, and then saying that would be a good estimate of what's happening at t equals 40.